So now we're going to look at conservation of momentum with two-dimensional collisions. Now remember, momentum is a vector. So like vectors, whenever we do two-dimensional things, we got to split everything up into its x and y component. And it has to be conserved in the x direction and the y direction separately. So two identical pucks collide in an air hockey table. One puck was originally at rest. If the incoming puck has a speed of 6 meters per second and scatters, so we got another puck here. It's moving at 6 meters per second. So this is before the collision. And then it scatters now this direction 30 degrees. What is the and they're saying this is an elastic collision. And they're telling you that the other puck, this second sentence is saying that for an elastic collisions, that if they have the identical mass, and they do have identical mass, the other one is going to move off at 90 degrees. So this would be 60 degrees here, this angle, okay? Because they need to sum up to 90 degrees, okay? Velocity, magnitude, and direction of the second puck. Okay, all right, so I think this is fine. I actually don't think we need to use this 60-degree result. We'll see. Let's say it's an... we'll kind of see here. So this comes in at 6 meters per second, all right? And so its initial momentum in the x direction is just 6m. It's m times 6 meters per second. And so that's the total momentum of the system. And there's no net force on the system. So that means after the collision, the momentum in the x direction ought to be 6. The momentum in the y direction is 0 because there's no velocity in the y direction. It's mass times the velocity in the y direction, no velocity in the y direction. And so momentum in the y also needs to be 0 in this case. Well, if this is moving at some velocity v, then the components of the x and the y direction of this vector are going to be v cosine 30 degrees and v sine 30 degrees, right? And so then we have to say, well, okay, I guess we'll have to use the result that this is 90 degrees. So if we say that this angle here is 60 degrees, if they move at right angles, and this is, we'll call this V1, and this is V2, then this velocity is also split into two components, V2 sine 60 degrees, and this one is V2 cosine 60 degrees. Okay. And so the momentum in the x direction, which has to equal 6, has to equal the total momentum in the x and the y direction would be has to equal 6m, by the way. That has to equal m times this velocity, which was v1 cosine 30 degrees, plus m times v2 cosine of 60 degrees. And then in the y direction, we need 0 is equal to m times v1 sine of 30 degrees. And what has to happen is this one is in the negative direction. If I say up is positive and right is positive, right? Then this one is negative, so minus m v2 sine 60 degrees. Okay. So I can first divide all the m's. The m's don't really matter. They'll all cancel out. And so this one is, so my equations are 6 is equal to cosine of 30 is root 3 over 2. V1 plus 1 half. Cosine of 60 is 1 half. And this equation is 0 is equal to V1 sine of 30. Sine of 30 is 1 half. 1 half V1 minus root 3 over 2 V2. And so I can, plug in for 1. If I look at this equation, for example, I could say V1 is equal to square root of 3 V2. And then I can plug that into this equation. So I have 6 is equal to root 3 over 2 root 3 V2 plus 1 half V2. That's 3 halves V2 plus 1 half V2. That's 2 V2. So V2 is equal to 3 meters per second. Okay. And then V1 is equal to what do we have? Root 3 times root 3 meters per second. Okay. Now to demonstrate that this is elastic, the energy must be equal, right? So the initial energy was 1/2 times m times 6 meters per second squared. That's 36. That's 18m. And then here, I would have energy of 1/2 m v1 squared plus 1/2 m v2 squared. That's 1/2 times m. v1 squared is 3 root 3 squared. That's 27 plus 1/2 m 9, and that's 36 times 1/2. That's 18m. Okay, so that confirms that it's elastic. Although it's kind of weird, we use this angle assumption here that for an elastic collision, that they were 90 degrees out of phase with each other. So, yeah. Okay. A 3,000 kilogram cannon is mounted so that it can recoil only in the horizontal direction. Calculate the recoil velocity when it fires a 15 kilogram shell. So I have firing a shell that's 15 kilograms at 480 meters per second at an angle of 20 degrees above the horizontal. Okay, so I want to know what the recoil velocity, there's going to be some velocity here, because together as a system, it had no velocity, and then we launched this out with some momentum. So the P before is equal to 0. The P after, if I say this is the X and the Y direction, along this incline, that means the velocity, this recoil velocity is going to be 20, downward, equal and opposite, basically, to make sure that it's 0, right? So the after, it's equal to 15 kilograms times 480 meters per second plus this thing can only recoil in the horizontal direction. I see. So this thing has wheels, and so it's going to recoil this direction, this velocity. So the way you want to do this is to say, well, what happened? Why is the momentum, like if I think about like the momentum before in the x direction is 0, and after in the x direction also needs to equal 0. What about the y direction? The y direction, the momentum isn't going to stay 0. Even though it starts out at 0, the final momentum in the y direction is non-zero, and that's because there must have been a normal force that was acting on this whole system. See, there's gravity and normal force. The most important is the normal force acting on this system. That would cause a change in the momentum in the y direction. Okay? And so that's why the momentum in the y direction is not conserved. Is because there is an outside force, namely the normal force, that's preventing this thing from going into the ground. Okay, and then this is 3,000. So going back to so I'm just doing the momentum in the x direction before is 0, because nothing's moving. And then after, this is heading out in some, I have to be careful, I have to look at its x velocity. Now, his x velocity is 480 times cosine of 20 degrees, right? Because if I split up his velocity, this is 480 cosine 20 degrees, and this is 480 sine of 20 degrees. So really, this velocity doesn't equal this velocity, but this momentum is going to equal this momentum here times v. And so I can solve for my v. It's equal to all of this divided by 3,000. So it'd be negative 15 times 480 times cosine of 20 degrees. All of that divided by 3,000. Negative 2.26 meters per second. Okay? And that makes sense. It's negative because it's the opposite direction. What is the kinetic energy of the cannon? The kinetic energy of the cannon is 1/2 mv squared. That's 1/2 times 3,000 times negative 2.26 squared. And so it has 7629 joules, 7,629 joules. What happens to the vertical component of momentum that is imparted to the cannon when it is fired? this vertical momentum is I don't know, it's reduced, shrinks to 0 due to normal force from ground. Okay, so the ground has to push an extra force in order to change the momentum of the cannon. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.